change the place, move it to some other part of the computer to compute, and then you can use this way to do it. So basically, the maybe another way to say that point is that Alice and Bob only need quantum channel in this state. And by quantum channel, I mean something that can send quantum information reliably. For example, telephone line is not a quantum channel. It's a quantum channel. It's not a good quantum channel. But then once Alice and Bob has pre-shared entanglement, the rest of the protocol, you just only need a telephone line, which I write by denote by double lines here. Yeah, actually tomorrow, yeah, is it tomorrow? I think we'll get to yeah, I want to talk more in depth about the notation of quantum circuits diagrams, so that we can to express things. Okay. Any questions about last time or? Okay. So yeah, no faster than light communication happens. So having entangled state here, this or this. If I measure one of the qubits, then I know the state of the other qubit instantly, because you would collapse the state to just one of the term, right? But is there anything wrong with this? It's usually like the selling point in news article about quantum entanglement, right? That if you have an entangled pair and you bring them to the two edges of the universe, and if you measure one of them, you know the state instantly. But if you just fix the basis of measurement for both sides to just one basis, then this is nothing, right? This is nothing different than just classical correlation. I can put, I can have a pair of globes which has left hand, right hand, and I can seal it in a box, and I can bring it to two sides of the universe. And if I open one box and I see left-handed globe, then I know instantly that I have the other box contains the right-handed one. So there's nothing weird about it. And so this was at a point in time, this was the point of contention that realist people like Einstein and Schrödinger kind of wonder whether you really need quantum mechanics, whether entanglement actually is actually spooky, or it's just maybe you can phrase it in terms of classical correlation. But then this the hope of that classical hidden variable theory is destroyed when Bell came along. So basically what Bell came up with, and later on improved by these four guys, Shimoni Hall, maybe, well, I don't know, is that they could find a scenario, so bipartite scenario, essentially that there's this Alice and Bob share an entangled pair, and then Alice makes a choice of measurement So let's choose a measurement. So basically, so we have 2 qubits here. So a measurement or a projective measurement can be in any direction on the block sphere, right? And that's what Alice and Bob can choose. In particular here, each person will have 2 choices. So A1 or A2, B1 or B2. And then Bell showed that there is a scenario or choice of measurements and state such that the resulting statistic of the measurement cannot be reproduced by sort of any theory with just classical correlation between the two parties or 2 qubits. And necessarily to build the statistic, you have to run this many times, right? Yeah. So the Bell experiment usually, yeah, you would have to do this, and then it's important that okay. So how would like a classical particle sheet this 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 kind of thing to reproduce the quantum statistic? Well, you would imagine that the particle would sort of like plan ahead, like have a meeting over here, right? Talk about well, if if you find if you see measurement A1, then what would you output as the answer? Or if you see the measurement A2, what would be output? So to do Bell experiment, it's crucial that the choice of this is the choice of measurement on both sides is made as late as possible. And naturally, you would want to have like Alice and Bob to be as far as possible, and then made the choice of measurement as late as possible in such a way that you can guarantee, assuming the speed limit of light, that there would be no communication between the two parties after the measurement choice had been set. Right? Because if the Alice and Bob are not far away enough, or if you make the choice kind of beforehand, before you, well, if you make the choice here, and the moment that Alice make a choice, you have a light cone here, right? And then if Bob make a measurement at this point in time, then in theory, is in principle, is possible, right? That the choice of measurements on Alice's side has been communicated in some way to Bob's particle. And so this would be something that you would want to avoid in experiments. And so people who did this original experiment got Nobel Prize 2 years ago, so 2022. Although at that point in time, I don't know, like 50 years ago, 40, 50 years ago, there at that time there was a lot of loopholes. Something, yeah, there's a bunch of things that could go wrong because the experiment, the state of the art of experiment at that time was not that good yet. And essentially, our loophole has been closed in experiment at Delft in Netherlands in 2015, using, I think it's a diamond, NV center in the diamond as well. They sent the qubit using photon, I guess, in like an optical fiber or something, and then convert that photonic state into spin state, and then make a measurement. Yeah, and the point is that they can at that time in that experiment they can switch this choice very fast. And well, yeah, this choice can be made by computer, right? Even though it doesn't need a list of Bob's free will. Although sometimes this is called a free will. It's like it's free will assumption, the assumption that the experimenter can choose uh, their choice of measurement, uh, because the ultimate hidden variable theory is that everything, including the choice of measurement, has already been determined since the time of Big Bang, and so there's no way to disprove that kind of theory. Oh, I shouldn't erase it. Sorry, Bob. Okay, so what exactly is this scenario? So in particular, I will describe the CSSS scenario, which was better suited to experiment, and that's what I guess almost all Bell experiments are actually based on. Okay, so in modern language, modern quantum information, this is usually phrased as a kind of non-local game, and this can be generalized to like more parties, more than qubit, and so on. So here, just to write that down again, there are essentially 4 choice of measurements. Okay, let's make sure that my notation is consistent. Okay. And then we'll specify that each measurement has only 2 possible outcomes. For qubit, it's natural, right? Because it's just 2 antipolar directions on the Bloch sphere. I don't know if I think I want 0 and 1 here. Of course, you can translate this to plus and minus 1 too, right? Yeah, so here the setting is that, for example, Alice can make a choice about which measurement she wants to make. But once she make a measurement, for example, A1, then there's 2 possible measurement outcomes. So this X and Y represent the measurement outcome regardless of the choice of measurement, right? And then the rule of the game is that, well, according to this picture, yeah, the rule of the game is that, well, Alice and Bob make makes their mind about what measurement they want to make, and then make a measurement, right? So A something, B something, and then I get a bit, a classical bit X and classical bit Y, and then there'll be a referee here who then compare these 2 classical bits. And then there's a particular rule. It's kind of arbitrary. It's not a fun game, right? It's just defined so that yeah, you can derive results. So the rule is the following. Okay, so I will write the obtuse one first, which will not be so clear what this means. So winning if the outcome is okay, this is a bit weird because here I sort of treat A and B as Boolean variables 0 and 1. Okay, so I think let me write down everything and yeah, just make sure that notation are the same. B. Oh. Yeah, because I think I switched my notation from the summer school, so I sort of have to switch everything. Right, so this is just basically multiplication, right? Well, so once A and B are chosen, then this is 4 possibility for the product, right? Well, and then this measurement outcome is not something you can control. It's statistical. It depends on also the state that you put in. So this rule, but to win, here I will need that these the value of x and y are the same, right? So that the parity of it, the mod 2 sum is 0, right? And this is true for all of them except this one. Difference. And so if I draw this as a diagram, so a list on this side. Okay, so I convert 0, 1 to 1, 2 again. Bob is on this side, so I think there's no brain shock. No. Find something that's easy to see. Right. So this say that for this pair of choice, for example, the outcome has to be the same. So if Alice and Bob make these choices, then to win the game, whatever outcome X and Y have to agree. So you use this orange line to mean agree. And the same for these other 2 pairs. Of course, I'm not considering like the pair on the same side, right? Because you cannot choose like these are incompatible. This could be incompatible measurement in general. You could like make a measurement in different direction on the block sphere. But then this last point means that if I want to win, then and then Alice and Bob choose the second measurement, then this have to this result has to disagree. And so because of this, you can sort of guess that there's really no way to deterministically win the game like all the time. So there's like what I would call like a frustration graph, because it represents conditions that cannot be satisfied simultaneously. If the last condition here require the result to agree, then this would be a trivial game, right? Because for every choice of measurement, the particle can conspire together, and then but they just say okay for any choice of measurement that Alice or Rob made, we just answer like 0, for example, all the time, and so they agree all the time. But if you do that here, the plan will fail 1/4 of the time. Okay. And that turns out to be the best that classical can do. how can I write this? Win classical. Yeah, and maybe you can, I guess one way to do this is just to exhaustively list all possible strategy that that Alice and Bob can do, or the particles can do, the hidden variable in the particles can do. And then also note that if you list out the deterministic strategy, right? That deterministic meaning that if given a choice, some choice of measurement, then what I would answer, what the particle would answer, then it's like I would just answer them all the time. There's no probability, but the point is that if you have an indeterministic strategy, the mixed strategy, then the probability of winning of an indeterministic strategy overall cannot exceed the maximum probability of winning for deterministic strategy. Because if I mix, so if I mix I don't know, strategy one with strategy one with the P, and then strategy two with probably 1 minus P, then this prefactor meaning that the probability of winning overall has to be average, right? And so it cannot the probability of winning of this kind of mixed strategy cannot exceed the maximum possible probability of winning for deterministic strategy, sort of the idea. But I'm not gonna prove here. But yeah, you might be plausible to convince yourself that the 3/4 is the maximum possibility of winning for classical. If you can share any classical correlation between the two spins. Okay, so here, what Bell or CSSS argue is that you can derive the scenario, the quantum scenario in which this probability is exceeded. So just let's make this little note here. And see, this is x, c plus x, c minus x. So I will send this state to Alice and Bob. And on Alice's side, I would measure these two directions, so C or X. So A1, so sigma A here denotes the a Pauli matrix on Alice's side. Here is just saying that the first choice is the C measurement. Then the second choice is the X measurement. For Bob, I would make the tilde measurement here. Say that the first measurement is the +1, and the square root of 2 here is just to make this a unit vector. Right? So maybe make it a unit vector so that the eigenvectors of eigenvalues of this is still plus or minus 1. Right. I need a lot of space. Any questions so far about the setting, about the... So now we're gonna calculate the probability of winning. So in this quantum case, well, so the probability of winning, well, there'll be 4 cases, right? So Alice and Bob choose their measurement uniformly randomly, and so each one appears with probably 1/4. So I have the average 1/4, everything in front. And now I would need to list all the probability of winning for different case, like, right? Okay, I want to be a bit lazy, just write P, and by this I mean probability of winning for each case. So here, for example, the first case is I measure, I just list every case, right? So condition on Alice making measurement 1 and Bob making measurement 1, the results are the same, right? And then you list all the possibility, right, of the choice of measurement. So this will be the same for every choice here, except just the last one. A2B1 and then plus P of X not equal to Y, A2B2. The closing bracket. Right. So how would you calculate each of this term? Let's see. I mean, maybe, but there isn't a more straightforward way, right? Because what we are conditioning on is just the choice of measurement, and so we really just calculate the Born rule probability, right? So this is the probability if I make measurement A1 and B1, then this is probability that, well, it has degeneracy, right? So it's probability that either this is true or this is true. And so you just need the projector of the two observable. How to say? So for example, if I what is the form of the observable? It's just the tensor product of those guys, right? So for example, if I have this one and this one, or rather any choice, right? If I have any choice of this, then each one of them has two projector, right? So corresponding to eigenvalue plus or minus one, and this as well plus or minus one. But what is the eigenvalue of this tensor product? What are like possible eigenvalue of this tensor product? Yeah, still plus because the eigenvalue of the total of the tensor product is the product of the eigenvalue, right? So the eigenvalue of this, so already taken care of, already separate the x equal y case and x not equal to y, right? Because if the eigenvalue of the whole, this is a case where the eigenvalue of the whole thing is plus one, and that this only term is a case where the eigenvalue is minus one. So we just need the projection operators onto the respective eigenspace. And well, and you can write this down pretty easily. So again, AB without subscript here, I just mean any AB. Right? So this would be the expectation value of okay. This right, or to just make it more explicit, this is the identity on the tensor product space. And maybe it look a bit long, but if you think back, then this is no different, right? So if I want an projector of z, for example, onto the like plus eigenvalue, then I just do this, right? Because the eigenvalues here are just plus or minus one, and if I want the operator onto the minus eigenspace, then I just change the sign, right? Yeah. And so I guess I'm not gonna write down the other case. If this is not equal, then I just change the sign here. Okay. So after some algebra, so here, so if I just plug this in, right, I will get a bunch of identity terms, and then a bunch of different like Pauli tensor product of Paulis. So here, for example, the identity term, I will get, so I got 1/8 here, just from 1/4 here, and then and then the factor of 2 here, right? And then I can collect, there are 4 copies of the identity operator. And then the other guy in here, which, okay, so let's do this. So of course, the expectation value of any operator, well, of the identity operator with respect to any state, it's just 1, right? So in particular, the expectation value of this, right? So I got 4 here. Then this guy, so now I just want to write out everything explicitly, meaning that I can replace these with the observable there, right? The linear combination of x and z there. And I'm just gonna write it down. Plus x. It's x, not enough space. X minus So here it's just algebra, right? It turns out that all the cross term cancel. So I have cx here and I have minus cx here. And the same goes for xz as well. So yes, x minus xz plus xz. So in the end, I got that I have 2 copies of everything. So I think this is one word. I missed the square root of 2 from there. So yeah, I would need square root of 2 here. And so in the end, I just get a nice little sum. Which if we want, we can go one step further and then note that using the identity of how to write this in terms of linear combination of projectors onto Bell state from last time. And here I already compensate with a factor of 2. This is, I hope this is correct. Which part should I erase? Well, maybe I don't need to erase anything. So here is should be correct. Here's the projector onto the faceless Bell state, the 0, 0 plus 1, 1, and then this is on the singlet state. So here, if I, as originally given, if I put in the omega 0, 0 state here, then only this term would survive, right? Right, and so only this term would be evaluated, survive and evaluated to 1, and so you get the final result that the probability of winning is this 1/2 plus 1 over 2 square root of 2, which is around this value, which is greater than the classical probability of winning of 3/4. So this is our magic, and you would work out something similar. Okay, let's. Can I erase this board? But just before we move on, so everyone is okay so far, right? Is it not? It's a tensor product. Yeah. Right here, everything is a tensor product, right? Okay, so we have devised a game that's admittedly probably not a fun game, but it shows that, well, at least based on this toy game that we just made up, correlation in, so quantum correlation or entanglement is seems to be stronger than classical correlation in some sense. Although interestingly, you cannot get probability 1 even in quantum mechanics. So let's us discuss the result a little bit more. So traditionally, Bell's inequality or CSHH inequality is phrased inequality is phrased not in terms of probability of winning a game, but just in terms of expectation value of this kind of operator. You can think of it as like two-point correlation function. Phrased in terms of the quantity B. Maybe it's another letter on Wikipedia, but here I would just, well, not, this is not a quantity, sorry. So B, this Metcalfe B would be some kind of bipartite operator. This is, yeah, generally just A, B, C, D are observable on the two parties. And the form here is exactly, well, it's made in, well, I guess historically it is the other way around. This is consistent, for example, the minus sign here with the minus sign over here, which express the probability of winning when two outcome has to disagree. And well, A, B, C, D can be anything in general. And the quantum bound is that the absolute value of this expectation value of this operator is 2 times square root 2, where classically this would just be 2. Sorry. So at this point there is no reason, but based on the modern way that we think in terms of non-local game, right? It's just the rule that the frustration graph here that I already erased is just the rule that one of the measurement outcome has to have to disagree on at least on both sides. So the other plus sign means that x is equal to y. So the outcome on the two sides agree. Yeah. So just to say, I guess it's worth saying the comment I made at the beginning again, right? If in the interpretation as the non-local game, if everything has a plus sign, it's a trivial game. Because, yeah. Although here it's not obvious, right? You sort of have to work backward because the minus sign here doesn't come from like the disagreement. The disagreement here is just the event here, right? But the minus sign come from the way that when you convert probability to how to say, when you convert probability of measurement outcome which is the expectation value of projection operator to expectation value of observables. And this is why how the, okay, I don't have the side of, this is where the minus sign come from, right? Okay, if I have x not equal to AB, then everything is the same except that I would have the minus sign here. Yeah, but the original derivation of the CHSH inequality or the Bell's inequality is really just algebraic. So they just say, okay, I have this Boolean variable, this 4 Boolean variables, and how can I arrange the equality or inequality in such a way that I can derive the classical constraint easily, and also that in the quantum case, I can exceed the value of it. It's really just some yes, there's some result that people want to arrive at to. I mean, before Bell, it was not obvious that quantum theory is not just classical theory. So if that is the case, if quantum theory is just classical theory, then there would be a yeah, any equality, any inequality that you would arrive that depends only on statistical result of statistical measurement would be able to, explain by just putting some classical probability theory there, some variables, some random variables there. So this bound is called Serialson bound, and there are many ways to write this. I think he's like Israeli or something. So here is Serialson bound, named after Boris Serialson, who just passed away a few years ago. And the relation to the winning probability, you can sort of see it from here, right? The winning probability in the quantum case is basically this. Right, because the square root 2 here come from the observable. And trying to study this bound more would be the subject of your homework problem. I think is fine. Okay. Maybe another thing that we can discuss is why not one. And I guess we don't really have a good answer. It's really the question of why quantum theory is true and not other theory. Interestingly, you can make up theory that have higher probability of winning. In particular, you can get the probability of winning up to 1, even though the theory is non-signaling, meaning that there's no faster than light signaling in the theory. So the kind of cartoon picture is sort of something like this. So Bell's inequality, this is a linear inequality, right? So you can choose, you can make different choices about observable here, and then there'll be some other state. So I choose this set of observable and the state specifically to make it look nice and make sure that I can get this value here, which is the maximum value. You can change like the observable, but then when you change the observable, the state that maximizes probability will change as well. And so in the point is that there are many Bell's inequality, and all of them you can sort of think of a phase of polytope. Okay, so what is this space that I'm talking about here? So what you can experimentally measure are really just these probabilities, right? And there are 16 choice of them. There are 16 probabilities. So because it depends on the binary value of A, of B, and of X and Y, right? So everything, so you can express these probabilities, this outcome probability, or you could say correlations in R16. There's some big space where each point is 16 probabilities of that kind. But of course, there's some trivial constraint that they have to sum to one and something like that, right? Have to marginalize correctly. So the cartoon is that for example, the inequality here would be the inequality that is like mark one, delineate one face of this sort of polygon in this space. This polygon is called the Bell polytope because everything inside is something that can be done, that can be accomplished by classical probability theory, by classical correlations. And then you have this set of quantum of probabilities that you can only get from quantum mechanics. So it turns out to be a convex set. So I would draw it like some ball here. This is quantum, and then the boundary here would represent the zeros and bound here. But you could also define other theory in the space of like all theory here in the R16 here that doesn't support faster than light communication. The jargon in the quantum foundations community that this is a no signaling theories. You could think of this theory as sort of just a black box that you put in value of A and B, and then it's spit out like X, Y with some probability. I've never read the proof, how they prove that it's non-signaling, but it's possible, and you can get this probability of winning up to 1. This would correspond to the zero-sum quantum quantity to be 4. Yeah, and I guess since then, so this is like 20 years ago or 15 years ago. Yeah, since then there has been researches, people study like why we don't have this kind of correlation in nature, for example, because it's non-signaling theory. Because it's non-signaling, it would not violate spatial relativity, right? So it's sort of a fine game, but somehow nature choose this particular like boundary of correlation that can be accomplished. Any question, comment? Okay. Well, I guess the best that I can explain is that black box. Right. So it's Well, I guess there's more, so I never studied this, so I don't know the detail, but uh, presumably, so really in the literature, this is called PR box. It's just the name of people, Popescu and Rolish. So basically, they define a black box that uh, you put in this classical bit, which represent like the choice of measurement that you make from party A and B, and then it can spit out some binary outcome X and Y, but in such a way it doesn't have to obey quantum theory. It doesn't have to be something that's possible to do in quantum mechanics. Uh, and then they somehow show that okay, even if you can get probability to winning just to one, it still doesn't violate no signal. You cannot use this correlation to send signal faster than light.
This is suppose we input A first time we input A one B one and output X is assume to be one and one two. This time we input the same output.
The same input or same output? Uh-huh. It doesn't have to be, right? Yes, like in quantum mechanics, this you cannot control this X and Y. It's random, but well, if you run it multiple times, you can find average, for example. Okay, how much time we left? 20 minutes. Okay.
It's so it look like a PR of low correlation. It's just random like random.
I'm not sure. Well, you have to think that this how to say this. So inside there's actually two parties, right? And there's a constraint that you cannot communicate instantly to each other. So like for Bell's inequality, if you think of like the classical scenario, you can put any randomness in there too. But you can the constraint that you cannot violate is that to communicate between two distant party, they have to have some finite speed limited by the speed of light. It's okay. Yeah, so that's how. So they must somehow incorporate the signaling condition into this somehow. Well, not signaling condition, but they must be able to prove, right, that whether this would allow you to send signal faster than light or not. Yeah, so if you're interested, you can search up PR box. There might even be a Wikipedia article on PR box, and I'm not sure. So before we switch gear to quantum circuit models tomorrow, yeah, and we meet tomorrow. Just remember 1:30 or 1. Yeah, 1:30 is fine. Yeah, and there'll be no class on Thursday. And I think that in the schedule I put on the website, next week there'll be makeup class, so there'll be 3 classes in total. Just to catch up with well, not catching up, but yeah, I will be away for like half of August. So, so I want to, yeah, before the end of this class here, just want to talk about uh, something that you would need in, I think, problem 3. So, if I have bipartite entanglement, in general, I can go here. I can, in general, is a linear combination of some, uh, some linear combination of the product basis, right? And again, this J and K, the number that J and K runs over don't have to be the same. So so this is Hilbert space A and B, this is Hilbert space A, Hilbert space B, and the dimension of A and B doesn't have to be the same. So the Schmidt decomposition is like kind of like a nice canonical form of bipartite entanglement that one, it reduces the sum to just one index, the sum over just one index. And then the second, which we'll talk about in a minute, is that is a form that you can is a form that tells you immediately the reduced density matrix of either the system A or B. In particular, the eigen you will get Schmidt decomposition will give you directly the eigenbasis of the reduced density matrix. So it's like it's not just any ensemble decomposition of the reduced density matrix, but it's the one in which all the pure state in the ensemble are orthogonal. But maybe first, let's try. So if I just want to reduce this sum to just sum over one index, well, what would I do? Well, maybe a first attempt, right, is just to define one of, maybe I can absorb, for example, define say fk, and let's see if I can pull out the sum into I can pull out the summation size through one of the ket, right? For example, if I pull it past EFJ and then just sum over K, right? I'll get some non-normalized vector in the second Hilbert space. And then, well, that would allow me to reduce the overall sum to just one, right? This is something you can always do, but it's kind of ugly. First is that there is an asymmetry in the first step, right? You will get a different form here if I choose to like group together vectors in B or vector in A. I have to make a choice, and I will have a different form over here. And also this other than non-normalized, also doesn't have to have any structure like orthogonality. Okay, so this is like first attempt. MPT. But the second attempt, well, the Schmidt decomposition says that we can do better. And that is to think of this CJK as a matrix and then perform singular value decomposition. So yes, I will have to sum over a new index. And so the singular value decomposition, right, will decompose a matrix into 3 parts. So there'll be a unitary on first and last. So make sure my index is okay. That's fine. And then there'll be a diagonal matrix in the middle, which I would call square root of p to be ready to what we're gonna get when we trace out the system. But this is just that this is what we know from HVD is that it's always positive, right? This is the singular value. And I never remember which one we call singular value or singular value square, but yeah, it's always positive. So yeah. In particular, p is positive, so I can take a positive square root. The positive square root is well defined. And then there is another matrix. So this is supposed to come from V dagger. So I have complex conjugate, and then I have to swap the 2 index. So it's not LK, but it's KL. So this is how you write a sum. So if I just to make it more clear. Right, so the sum over L of this whole thing, right, is the JK element of this product of matrix, where this is the diagonal matrix. Right. If you sum over L, then cannot forget the basis vector. Okay, so that's nice. But notice that now I can combine this matrix element with these basis vector, because these are from SVD, we know that these are unitary. So the hope is that, well, if it comes out correctly, then you can put all the sum together. It will just be turn to be a unitary transformation on the basis which produce another orthonormal basis. So I still have L, L, and then here I want to sum over J, EJ, UJL, sum over K, FK, V star, KL. If V is unitary, V star is also unitary. And so now I can, okay, now I can be fancy and then call this new L. This is a orthonormal basis for Hilbert space A. And then I call this new prime L. And this is, again, O and B for Hilbert space B. Well, or maybe more correctly, these are orthogonal set. Right. Whether they span, whether we have enough vectors to span each vector will depends on the state here, right? But one thing that I can say, so maybe I should write this down. So overall, with the sum with a positive coefficient of something uh, with some orthogonal vector nu L, nu prime L. But note that at most L can run from 1 to just the whatever is the dimension that is whatever the smaller dimension. Right, because the sum now has only one index. If I say, for example, if the first Hilbert space is just a qubit, there would just be new 1 and new 2, right? There'll just be 2 elements of this, and you cannot extend the sum anymore. Even if you can have like infinite dimensional Hilbert space over here, but the sum would just there'll just be 2 terms in the sum. Yeah, and this is the Schmidt decomposition. What can I say? The nice thing about it is that if I want to calculate the reduced density matrix, which is to say if I trace out one of the system and then look at the density matrix, right, that I get. For example, if I suppose I trace out system B, what would I get? I would just calculate the trace in this or in these orthogonal basis, right? In the new basis, well, not the new and the old, but the Greek letter new basis, and then I would just Q off all the off diagonal term. So I have L, new L, and then I have the square of these. So this is precisely eigen decomposition of the reduced density matrix of system A. And you can notice that, so this is row A. You can notice that if you switch the row of A and B, you pretty much also get pretty much the same thing. And again, this gives you the eigen decomposition of row B, with a really nice result that both row A and row B has exactly the same spectrum, same eigenvalues. Maybe I can add more. So this is also L is the rank of, well, of course, it's the rank of B. I think it's the same as the rank of CJK also. I'm not sure, but it's just the number of non-zero singular value, right? Yeah. So basically, this is how many non-zero PL. Okay, it's already noon. So for homework problem 3, in homework set 3, you will be asked to think about Schmidt decomposition of 3 parties. Okay, do I have any more comment? I'm not sure. Do you have any more comments or questions before leaving the class? Yeah. Yeah, the question would be, can I write the sort of 3 thing in like tripartite space in this form? Okay. Well, it turns out that you cannot. That's why I have a question mark in my problem set. in the name of the problem. Yeah. I mean, and this thing is used to define matrix product state too, right? But then I guess we can talk about that once we get to tensor network. Right. Okay, so this Thursday and Friday, I guess the faculty here will be away somewhere. So if we have car accident, then nobody will come back, and you don't have to take any more class. But I hope that next week, once I like says enough things about quantum circuit model, I can come back to use a circuit model to describe something called quantum eraser. Yes. And maybe it's a little informal homework is that if you don't know what quantum eraser is, I suggest you to try to see what can you find out on the internet, what they are, before I talk about next week. It's probably help with, that, yeah, it will probably enhance your understanding a bit if you know it before. The fun thing about this is that there's a lot of misconception about quantum eraser on the internet. So yeah, so I just want you to look at it to see what you get. Yeah, in particular, a lot of people say that quantum eraser let you to change the past. There's YouTube video on this. Yeah. So yeah, we'll see exactly what happened next week. ไม่แน่ใจมีสไลด์อะไรที่ทำค้างตั้งแต่2 ปีที่แล้วผมก็เลยทำต่อเมื่อคืน